Welcome to the Explainer. I want you to imagine, for just a moment, that you are not walking into a quiet, stuffy exam hall. Let's completely reframe this. Instead, you are stepping right onto a high-stakes, incredibly intense trading floor. The clock is ticking relentlessly, the pressure is absolutely immense, and the noise in your head is deafening. Every single minute you have in that room is capital. It's your investment, and you need to make split-second decisions on exactly where to invest your time to get the absolute highest return on investment possible. The currency we're dealing with here? It's marks. Your market? The Cambridge Physics Syllabi. Now, whether you are sitting for the 0625, 0651, 0652, 5554, or even the advanced 9702, the rules of this trading floor are exactly the same. Today, we are focusing on one of the most volatile yet highly predictable assets you're going to encounter on this trading floor, Radioactive Decay 1. Okay, let's really dive into this. We are going to decode exactly how Cambridge examiners think, how they physically structure their mark schemes, and most importantly, how you can guarantee your maximum return. We're moving way beyond just passively memorizing textbook pages. We are going to build a rigorous, strategic framework that ensures absolutely every sentence you write literally prints marks on your exam paper. Welcome to your ultimate physics exam strategy session. Let's maximize that portfolio right now.
Now, what's really genuinely interesting about our approach today is that it completely flips the traditional, boring way we learn physics completely upside down. Seriously, think about how it's usually taught. You get a list of definitions, right? Instead of starting with those dry, isolated definitions of alpha, beta, and gamma radiation, we are going all in on an application-first method. Consider this core, fundamental question. What physical effect, measurement, or prediction actually depends on understanding radioactive decay? Before we even touch the formal physics vocabulary or the complex equations, you need to understand the why. Why on earth does this matter? If you can't anchor the scientific concept to a real-world necessity, I guarantee you those abstract formulas will slip right out of your mind the second exam pressure hits. The source material emphasizes this brilliantly. A solid, unshakable understanding begins with a simple question that makes the idea feel absolutely necessary rather than just decorative knowledge. By starting with the concrete physical effects, like how a Geiger-Müller tube actually clicks in your ear, or how a medical tracer physically maps blood flow in a human body, you become far less dependent on memorized wording. You stop acting like a robot, desperately trying to recall a textbook paragraph, and you start actively reasoning your way through unfamiliar, high-level exam questions. And listen, that reasoning, that is exactly what secures the top grades in any Cambridge paper.
Let's move along and see exactly how this builds by looking at two very classic student archetypes on our trading floor. Honestly, we've all been an Alex or a Sam at some point. They both studied incredibly hard, spent hours at the library, but they are both hemorrhaging marks. They are losing their investment completely. Take Alex, for example. Alex's go-to strategy is the classic data dump. When asked a highly specific question about decay equations, Alex panics and overloads the page with raw facts, listing the ionizing power, the physical range, and the charge of alpha and beta particles. But Alex completely fails to build a logical cause-and-effect argument that actually answers the specific prompt. The examiner reads it, sighs, and gives 0 marks for a paragraph of irrelevant, perfectly true but useless information. Then we have Sam. Sam is the formula master. Sam memorizes equations perfectly and rushes through the paper. Sam throws down a highly complex decay formula, perfectly remembered. But here's the tragedy. Sam loses the marks because, as the source points out, a massive exam weakness is writing the correct formula without explaining the variables. If you don't explicitly state what each and every symbol represents in the exact context of the specific question, the examiner simply cannot award the marks. Both Alex and Sam completely miss the command word requirements. They miss the strategy. Don't be an Alex, don't be a Sam.
So you're probably asking, what is the winning strategy? How do top-tier students consistently pull A-stars out of this volatile market year after year? It's not magic. They use a highly structured, repeatable system. I call it the 4-step physics blueprint, and it's mapped directly to the Peel framework. This is derived straight from our source's explicit guidance on how to visually structure a secure, unassailable answer. Step 1 is the point. Identify the exact quantity, phenomenon, or core idea. Define it clearly and immediately. Step 2 is evidence. State the specific physical relationship involved, whether that's a written equation or a direct proportional link between two variables. Step 3 is the explanation. Unpack the underlying physics. This is the crucial part. This is where you bring in the cause and effect chain. Why does the relationship hold true? Step 4 is the link. Connect it to an actual observation, an experiment, or a real-world device. In Cambridge IGCSE style physics, the absolute best, undeniably top-tier answers demonstrate both deep theoretical understanding and clear practical application. If you can visually walk your examiner through these 4 sequentially linked steps, identify, state relationship, explain underlying physics, connect to reality, you are literally handing them a flawless marking key. You are doing their job for them, and they will reward you with maximum marks.
Okay, it is time to put your money where your mouth is. Let's test your eye on the trading floor. We have an interactive challenge for you right now. A visual timer is starting for 30 seconds. I want you to mentally review an exam answer you recently wrote, pictured in your head. Did it honestly contain the point, the evidence, the explanation, and the link? Can you actively spot which parts of your own answer were missing? While you think about that and audit your own personal exam strategy, consider where your natural blind spots are hiding. Do you naturally rush straight to the explanation and forget to define the core idea first? Or maybe you state the correct formula but completely forget the real-world link at the end. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, your time is up. If you just realized your answers usually just stall out at the point or evidence stage, congratulations, you now know exactly where your missing marks are hiding. You've got to push all the way through to the explanation and the link to unlock those elusive highest grade bands.
Let's focus intensely for a moment on that final critical step of the Peel framework, the link. The source material makes a massive, undeniable point about grounding abstract theory in concrete reality. Remember, radioactive decay isn't just some hypothetical thing that happens on a dusty chalkboard. It is the fundamental driving mechanism behind multiple global industries. Radioactive decay literally appears in engineering for measuring material thickness precisely. It aggressively dictates protocols in the safety and transport of hazardous materials globally. It is the absolute core of our massive nuclear energy systems. It has completely revolutionized medical technology, from targeted cancer radiotherapy to incredibly precise diagnostic tracers flowing through veins. It even acts as a grand cosmic clock in astronomy through radiometric dating. As a top-tier Cambridge candidate, you must always, without fail, be able to confidently name at least one real situation where the concept matters. But listen to me carefully. Don't just randomly name-drop it. You have to explain exactly why the physics helps us predict or improve outcomes in that specific field. That explicit justification is the secret ingredient that turns a solidly good physics student into an absolutely exceptional one in the eyes of the examiner.
Let's actually look at this blueprint in action on a real paper. We are doing a live answer transformation right now, so pay close attention. Consider this heavily flawed answer, currently bleeding red ink all over the page. Beta decay happens when a neutron turns into a proton and an electron. It is used in paper mills. Okay, why is this answer bleeding marks? Because it's literally just a disconnected string of memorized facts. It quotes a decay process but completely fails to link it to a physical effect, and then it randomly slaps an example on the end without showing why it logically follows from the physics. Now, compare that disaster to a top-tier, fully linked, beautiful answer. During beta decay, a neutron transforms into a proton and a fast-moving electron. That is your solid point and evidence. Because beta particles can physically penetrate paper but are partially absorbed, the count rate detected on the other side physically changes if the paper thickness varies. Right there is your deep explanation. Therefore, a computerized feedback loop can actively adjust the rollers in a paper mill to ensure completely uniform paper thickness. And that wraps up the undeniable link. Do you visually see the profound difference there? The cause and effect chain is flawless. We just effortlessly turned a measly 1-mark answer into a robust 4-mark answer just by connecting the dots.
And this transformation we just did brilliantly illustrates the golden rule pulled directly from the chief examiner's desk. Listen to this quote. Insist on cause and effect rather than isolated facts. If you take absolutely only one single thing away from this entire explainer session today, let it be this exact, precise quote. It's a game changer. When you are dealing with fields, powerful forces, subatomic particles, complex circuits, or waves, and particularly when you're wrestling with radioactive decay, isolated facts are basically completely worthless currency. The examiner is emphatically not testing your ability to be a human dictionary. No. The examiner is testing your ability to be a working physicist, and a physicist intrinsically understands how A physically causes B, which ultimately results in C. You must never quote a decay process without explicitly physically linking it to its tangible effect. Never give a real-world example without showing the exact step-by-step physical mechanism that makes it actually work. If your sentence doesn't have the word because or therefore in it, you need to stop, look very carefully, and ask yourself whether you are actually explaining the physics or just blindly listing facts. Cause and effect is your ultimate impenetrable shield against losing marks. Let's take a very quick, strategic mental breather to really let all of this powerful framework sink in. The fundamental difference between sitting in that hall struggling to recall raw facts and sitting there confidently analyzing a complex problem comes entirely down to that Peel blueprint we just thoroughly walked through. When you are at your desk studying your past papers, do not just casually check if you got the right final number at the bottom. That's a trap. Check if your underlying logic naturally flowed. Did you firmly establish a point? Did you provide the indisputable evidence? Did you logically construct the explanation with a solid because statement? And did you securely lock in the final marks with a real-world link? Getting into the strict habit right now means that when the intense exam pressure inevitably hits, you won't be scrambling in the dark for disconnected facts. Your brain will automatically, instinctively default to this structured, high-yield system. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, shake it off. We are right back on the trading floor, and it is time for Challenge 1 of our interactive workshop. I call this the high-speed data scan. Right here on screen is a classic Cambridge-style radioactive decay data table. You have exactly 60 seconds of simulated, intense exam pressure to look at this table and extract the core decay trend. Go. Mentally lock in. Look closely at the columns. Time in days, activity measured in becquerels, mass in grams. What is the fundamental underlying pattern hiding in these numbers? Look at day 0. We start with an activity of 8,000. Fast forward to day 5, and it drops exactly to 4,000. At day 10, it drops again to 2,000. Now notice how the physical mass perfectly, elegantly mirrors this exact halving process, dropping from 100 to 50 and then down to 25. The core, undeniable trend you need to spot instantly here is the half-life. It takes exactly 5 days for the activity and the physical mass of the undecayed isotope to systematically reduce to half of its initial value. If you can train your brain to scan complex datasets like this and immediately pull out the underlying physics principle, you will save yourself precious minutes of sheer panic in the actual exam room. You'll be calculating while everyone else is still reading.
Let's immediately move to Challenge 2, Find the Flaw. I want you to listen to this incredibly common 2-sentence answer. Alpha decay emits a particle, the mass number changes. This is exactly the kind of rushed, panicked answer a student writes when they're watching the clock and feeling the pressure mount. So the absolute crucial point is this. Why is this specific answer bleeding marks? What is the fatal underlying flaw here? Think back to the examiner's note we just discussed a few minutes ago. The massive flaw here is that it presents 2 entirely isolated facts with absolutely zero cause and effect chain linking them together. It completely, totally ignores the explanation part of our mandatory Peel framework. To fix this, you have to actively connect the dots for the examiner. A top-tier, maximum mark correction would read like this. Alpha decay emits an alpha particle, which physically consists of 2 protons and 2 neutrons. Because the original parent nucleus physically loses these 4 nucleons, its overall mass number mathematically decreases by exactly 4. Do you see how we confidently introduce the specific physical mechanism, the literal loss of 2 protons and 2 neutrons, to explicitly explain why the mass number changes? That is the rigorous cause and effect the examiner absolutely demands.
Now it's time for Challenge 3, Speed Writing. This is where we actively forge diamond-level exam skills under immense pressure. You have exactly 30 seconds to mentally construct or frantically jot down on a piece of scrap paper one single perfect Peel paragraph explaining exactly how gamma radiation is used in medical sterilization. The clock is ticking. Remember your blueprint. Point. Define what gamma radiation is. Evidence. State its extreme penetrating power. Explanation. Dive into the physics of why it successfully destroys bacteria DNA without making the actual medical equipment radioactive. Link. Conclude with a strong therefore, showing why it is the absolute ideal choice for sterilizing sealed medical tools. You absolutely have to be able to pull this framework up instantly in your mind. The real difference between an A and an A star isn't just vaguely knowing the physics, it's the raw speed and clinical precision with which you can communicate that complex physics under a brutally tight time constraint. Practice the speed writing drill daily. Seriously. Take any microtopic from your syllabus, ruthlessly apply the 4-step framework, and race the clock. It will completely, utterly transform your exam confidence.
To make absolutely sure you never ever draw a terrifying blank in the exam hall, our source material provides these 4 brilliantly simple physics exam memory prompts. Look at these. This is your ultimate pre-game cheat sheet for any structured question. Whenever you face a daunting 3, 4, or 5-mark question on radioactive decay, aggressively ask yourself these 4 questions aloud in your head. 1. What is the core idea? This forces your brain to identify and define the phenomenon clearly before you start rambling. 2. What changes physically? This specifically prompts you to state the exact relationship or the required equation. 3. What graph or diagram shows it? This visually pushes you to explain the underlying physics conceptually. 4. Where is it used? This absolutely guarantees you hit the application and link marks that everyone else forgets. If you can reliably answer these 4 prompts for every major topic in your textbook, your knowledge base is mathematically, undeniably secure. You are just crossing your fingers and hoping to remember you have installed a systematic fail-proof retrieval protocol in your brain.
Let's come back to center and focus on one absolutely crucial number, 0625. This is the Cambridge IGCSE physics syllabus code. It is not just a random test. It is a highly specific system with highly specific rules of engagement. The strategies we've rigorously discussed today, actively decoding command words, ruthlessly applying the Peel framework to every long answer, aggressively insisting on cause and effect chains, and using the 4 memory prompts under pressure, these are entirely precisely calibrated for this exact syllabus game. You are not just casually learning general science here, you are actively learning how to completely dominate the 0625 game. If you respect this system, decode the examiner's command words carefully, apply your structured blueprint to every single extended response question, and manage your time matrix effectively on that trading floor, you practically guarantee top marks. The examiner's incredibly strict mark scheme is a lock, and the Peel framework is quite literally the only key that turns it smoothly every single time.
So, as we finally close out this intense session on the trading floor, I want to leave you with one final, deeply provocative question. Can you mentally construct your next perfect radioactive decay answer right now? Can you literally feel the rigid structure of point, evidence, explanation, and link naturally forming in your mind before you even pick up a pen? Because if you can visualize that, you are truly ready. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.